Good afternoon, everyone. Let us start with next unit, that is unit number 4, and this is about the deadlocks. So first of all, am I audible, and can you see the presentation I shared? Okay, no problem. So now let us continue with this unit. Even though 7 is mentioned, this is from the book actually. So unit number 4. Now what we are going to discuss in this is we need to define some sort of a system model for representing deadlock. Then we need to see different characteristics of deadlock, then how to handle the deadlock. Is it possible to prevent the deadlock? So few algorithms are there for deadlock prevention. Deadlock avoidance. So again 2-3 algorithms are there. And if deadlock is allowed by the system, we need to detect if there is a deadlock or not. And if there is a deadlock, we need to see how to recover our operating system from the deadlock. Okay. These are the contents we want to discuss. The objectives for this deadlock is to, first of all, we need to define what is deadlock. I think in unit number 1, I just mentioned there is a deadlock. Even in case of inter-process synchronization also I mentioned about the deadlock, wherein we saw if we use semaphore in wrong way, then it may result your system in deadlock. Okay, so we need to define what the deadlock is. So that part first of all we'll see, and then we need to see, for example, is it possible to prevent the deadlock? Okay, and we need to see different methods for avoiding the deadlock in our computer system. Actually, this unit deals with so many algorithms used for different stages of deadlock. So in that part we'll see. Let us start with the system model, or even before this, let me share the whiteboard. Okay, and now we'll try to define what is the deadlock. Okay, now so for the deadlock we need to understand, like for example, in my system there are few processes. So process is one part. Next we have some called as resources, right? And like for example, again if I repeat the example of dining philosopher problem, now what happens in that is, say for example 5 philosophers are there and 5 chopsticks are there, and everybody picked up one chopstick, right? Now what will happen is, what is the problem with that approach is, nobody can now eat the food there, because everybody is holding one chopstick and waiting for another chopstick. In very generic situation, I can say there are processes holding some resources and waiting for some other resources, or maybe another units of resources. And what happens is, maybe that will create some sort of a circular wait. It's not like always circular wait, but one of the very simple thing to understand is like circular wait. Okay, and that circular wait will result in deadlock. Okay, so for example, if I draw something here, for example, let me draw, this is one process, this is process number 2, and let me draw, this is process number 3. Let me give names like say process 1, that is P1, process 2, and process 3. Okay, and situation may arise something like P1 is holding some resource and that is required by, let me write something like this. P1 holds some resource, P2 holds some resource, and P3 holds some resource. And P1 is holding some resources. And P2 needs required by, hold by P2. P2 already has some resources and they need something that is held by P2. And P3 also got some sort of resources and it is waiting for some more resources. See how circular weight is represented like this diagram. Okay, so P1 holding some resources required by P3 and P1 needs some resources held by P2. Similarly, P2 require resources held by P3 and P2 holds resources required by P1. Here you need to understand the direction of arrow. Now P2 is pointing to P3, that means P2 holds some resources that are required by P1 and P2 requires resources held by P3. So you can imagine like it's kind of a request kind of a age from P2 to P3. Now what happens is P1 is not making progress because it is waiting for resources of P2. P2 is not making progress because it is required resources held by P3, and P3 also cannot proceed, not making any progress because it is waiting for the resources held by P1. So everybody is holding some resource and waiting for the resources held by others. Now what happens is not a single process making progress. P1, P2, P3, everybody is just in waiting state. And this situation is called as deadlock. This is called as deadlock. Okay. So this is again you try to map the same diagram for dining philosopher problem. Consider 3 philosophers are there, 3 chopsticks are there. Okay. So P1 got 1 chopstick, P2 got 1 chopstick, P3 got 1 chopstick. So now P1 is waiting for chopstick by P2, P2 is waiting for chopstick by P3, and P3 is waiting for chopstick by P1. Nobody is making progress in order to eat the food there. Right? So that is what deadlock is. Not any single process making progress. Everybody is just waiting there. Okay. So let us go back to the presentation. Right. Now we need to define some sort of a system model. Okay. And that will model the situation of deadlock in more sophisticated way. Okay. Now this slide talks about resources. Operating system has so many resources, even though multiple types. Now here when we say resource, we need to concentrate on 2 parts. One is how many instances of that resource is available and what are different types of resources are there. So for example, in real desktop operating system, maybe you have multiple files, some RAM blocks, maybe some sort of sockets, maybe some sort of ports, multiple printers possible, or maybe single printer, or maybe there is not at all any printer available there. So all these are like input output devices. You can imagine like that as the resource. Not only that, even though you have a single processor in your operating system for your PC, say for example, then whatever the time of that processor, usually called as CPU cycles, that is also one of the resource type. Imagine like there are 10 processors and some sort of round robin scheduling is there, and some say 10 millisecond is the time quantum. Okay. Now one slot of processor is also called as a resource. Okay. Resources are denoted by R. So let me try to write it here. R. It is very small, so it is something like this, R. So these are the resources. In general, we'll denote it as Ri. Okay. Now this is resource type. So for example, if there are three printers, we don't call it as R1, R2, R3. Try to understand this. When I say print file, I'll say simply R2 denotes the printer. It denotes the type of resource. And when you're talking about 3 instances of this, now that will be denoted by W. So W of I, this denotes number of instances for that resource type. So notations to understand. So very first thing is your operating system consists of multiple resources, and these resources can be grouped as a resource type. Each and every resource type is denoted by some alphabet, something like R1, R2, R3 up to Rm. So my operating system consists of m types of resource. So if there are say 10 resources, I can say 1, 2, 3, R1, R2, R3, R4 up to R10. Here upper limit is m. Okay. So m denotes number of resource types, and out of that individual resource types will be denoted by R1, R2, R3 up to Rm. Okay. Let us call in generic way Ri. Okay, so that is the resource type, and for each resource type there will be number of instances. So for example, as I mentioned, if R2 denotes the printer, and if there are 3 printers, then I can say R2 has 3 instances, and that will be by Wi, number of instances. So W2 is equal to, so let me write that as an example here. Let me go back to the whiteboard. Suppose R2, this denotes printer, and if there are 3 printers, we'll write W2 is equal to 3. Okay. So R2 denotes the category, rather I can say, and W2, this denotes number of instances. If there is a single printer, it could be 1. If there are no printers, we may write instance equal to 0. Rather I can say in that case there is no need to mention that as a resource type, because which is not available there, right? Now each process utilize a resource. We know like a critical section. For example, first upon a process is denoted by P. So ith process denoted by Pi, something like this. Okay. So Pi will first upon make request. Now request to operating system, because operating system acts as manager for resource management. It could be hardware resources, it could be your file system, it could be memory space, it could be IO devices, anything, any type of resource. Okay. So process first of all makes a request to the operating system, and if operating system grants permission to use that resource, process PI will use the resource. Process PI will use of that resource, and once process done using that resource, it must be released so that it will be available to other processes. Okay, so remember the resources are shared amongst all the processes, and because it is shared, whenever you want to use that resource, first of all you need to check if somebody else is using it, right? Who will manage this? Operating system acts as a manager for that, and that is the reason you cannot directly send, say for example there is a printer, you cannot directly send your document to the printer for printing purpose. Reason behind that is very simple, right? If anybody else is already using it, you should be waiting in the spool. That is called as a spool actually for a printer. Okay, so the protocol in order to use the resources is very simple. Make a request. If it is granted by operating system, use that resource. Once you're done using it, release the resource. Any doubt in this? And don't get confused between resource types and number of instances of that. So instances will be denoted by W capital, and resource types will be denoted by R capital. Processes will be denoted by capital P, right? Fine. So let us move to the next slide. Now we need to first of all specify the characteristics, or rather I can say we need to discuss the conditions. One of the thing I already mentioned, something like circular weight. Now what are the conditions if these arise at the same time simultaneously? Then there is a possibility of deadlock. Okay, let us start with first condition. It is mutual exclusion. Now why this condition is required? See, we are aware of what is mutual exclusion. Like when we studied about the critical section, we have discussed this mutual exclusion. Only one process at a time can use that resource. Same thing I mentioned for critical section. Updation of shared variable can be done at most by one process at a time. So no simultaneous updation, right? And that updation we call it as a critical section, and that is the reason we always say there should be only one process at max in the critical section. How to do that? We already discussed so many algorithms for that, making use of some sort of semaphores. Now imagine if mutual exclusion is not there. For example, if anybody can directly use the printer without checking if anybody else is using it, right? That means the resource is not serializable. If there is no need to wait, deadlock will not be there. Okay, so that is the case. So very first thing that is required is mutual exclusion. So one of the possible condition or reason for deadlock to arise is mutual exclusion. Whatever resources are there in the system, they must be used one after other. Only one process at a time can use the resource. That is called as mutual exclusion. Condition number 1. Condition number 2 is hold and wait. Okay, hold and wait is what? Like in circular wait I just mentioned, even in dining philosopher problem, hold and wait is what? For example, I am holding one chopstick and I am waiting for another chopstick. That means I already holding some resource, maybe at least one resource, and I am waiting to acquire additional resource. And that additional resource required is held by somebody else. This situation is called as hold and wait. It is not just wait. Okay, because if you are holding something, then and then only it will go to the circular wait. Otherwise, say for example, if you are waiting something, if you are not holding, no problem. There is a guarantee, like maybe in some finite amount of time, somebody who is already using that resource will finish its work, and that resource will be available for you, and then you will continue. Right? That don't happen in case of deadlock. In deadlock, what happens is nobody is making progress. I'm not, say for example, there are 5 processes and P1 is just waiting, or say or P1, P2, P3 are waiting, and P4 and P5 they are making progress. And why P1, P2, P3 are waiting? Maybe the resources required by P1, P2, P3 is held by P4 and P5. If they are making progress, no problem. Even though P1, P2, P3 is waiting, time will come where P4 or P5 will finish their task and resources will be released. Why resources will be released? That is what the protocol I suggested on previous slide. Whenever you want to use resource, first upon request for the resource, use it. Once you're done with that resource, release it. So P4 and P5 will release the resource, and then P1, P2, P3, maybe P1, maybe P2, depending upon which one is scheduled first, will be waken up and they will make progress towards their completion. That is possible. But there are chances of deadlock, rather I can say more chances of deadlock when you hold some resource and waiting for some additional resource. This condition is called as hold and wait. Not just wait, hold and wait. Okay. This is condition number 2. Condition number 3 is no preemption. No preemption. In scheduling also we come across this preemption. That is specifically with the processor, but here it is now in general for any resource. The meaning of no preemption is resource can be released only voluntarily by the process holding it, not forcefully. Remember, not forcefully. Because preemption is like, for example, if one process is already executing and higher priority process arrives there, that on arrival of that, the currently scheduled process will be interrupted. Now that becomes forceful thing. That is called as a preemption. Here what we need is no preemption. That means, say for example, again let us come back to the dining philosopher problem. If 3 philosophers are there, 3 chopsticks are there, one philosopher cannot forcefully take the chopstick from another philosopher. This is called a no preemption. Okay, that means there is nothing like a priority. Okay, so this is condition number 3. No preemption. Next condition is circular wait. I just mentioned that I simply drawn that diagram here. Now, in more sophisticated way, more technical way, this is represented like we have a set of processes. Say n processes are there, P0, P1 up to Pn. Rather, I can say n plus 1 because the number started with 0. Okay. So there are a set of n processes and they are waiting such that P0 is waiting for resource that is held by P1. P1 is waiting for the resource held by P2. P2 is waiting for the resource held by P3. So on so forth, like say second last, like P of n minus 1, that process is waiting for resource held by Pn. And Pn, that is the last process, is waiting for the resource held by P0. So that creates like P1, say if it is say 5 processes, P1 is waiting for P2, P2 is for P3, P3 for P4, P4 for P5, and P5 is waiting for first one, P1, right? So this situation is called as, or this condition rather is called as circular wait. Okay. So this is also called as necessary and sufficient conditions for deadlock to occur. Mutual exclusion, hold and wait, no preemption, and circular wait. Okay. Any doubt? So there is question on what is this? Deadlock. Okay, you written in Marathi. Deadlock साठी या सगळ्या condition because याला arise while, yes, exactly. That is the very first statement. Your question is correct. The same thing is mentioned here. If these 4 conditions hold simultaneously. See, in circular wait itself talks about hold and wait, right? Like P1 is holding something and waiting for P2. P2 is holding something which is required by P1 and waiting for something held by P3. So circular wait itself is like hold and wait. Okay. No preemption because we cannot take forceful, and mutual exclusion because that resource has to be used one after other. So all these 4 conditions must hold simultaneously. That is the answer to your question. Okay. Any questions there on these 4 conditions? See, these are necessary conditions and sufficient because if all 4 are there, deadlock is there. That is the reason both the words are used, necessary and sufficient. Right. So let's move to next. Now deadlock can occur via system calls and locking also. One of the example is given, like for example, I think I mentioned this part last time. Say for example, there is a resource and in order to access that resource, whenever you want to go into the critical section, first of all we make use of wait on lock, right, or wait on semaphore variable. So something like we use like this. First upon wait, then there is a critical section, and then there is a signal. Right. Now what will happen if process acquired semaphore, used it and forget to release it? What will happen is definitely if any other process is there, not necessarily other process, if this process is also in a loop, this also will not get access because with when we modified the value of semaphore variable, say for example from 1 to 0. So latter time if you again execute wait, it will sense the like value of that semaphore variable is equal to 0. And if that is 0, it has to wait there. So maybe process will lock itself. So not necessarily the resources of different kinds. Maybe mutex locks are also called as resources. So you can imagine that as a separate resource. Now, in order to represent the state of the processes and resources, in order to check if results in deadlock or not, one of the simplest way to represent current state of the system is making use of resource allocation graph. Resource allocation graph. Okay. I think you already gone through the graph data structure. The same thing. Now, only thing is we just need to give meaning to the vertices. If you remember, graph G is defined as, what is that? G is equal to V comma E. Let me move to the whiteboard. Let me use this text box. Graph G is written something like this. G is equal to set of V comma E, where itself V is what? Set of vertices, and E is what? Set of edges. Okay. Now, in resource allocation graph, a set of vertices V Hello, am I audible now? Check it. Okay, okay. Uh, so let me repeat the same part just I mentioned on this slide. Graph G is called as G is equal to V comma E, where V is set of vertices and E is called as set of edges. Right. Now, the V is partitioned into two types. One is for processes and one is for resources. One is processes. So processes are numbered like P1, P2, P3, P4, P5 up to Pn. So there will be n number of processes and m number of resource types. Again, don't get confused here for m. So here there are n processes and there are m resource types. Right. So R1, R2 up to Rm. So m resource types are there. Now there are two types of edges. One is called as request edge and one is called as assignment edge. Remember, both are directed. That means we must have an arrow for that edge. If that arrow is from P to R, if that arrow is from P to R, meaning of that is process Pi is requesting for resource Rj. So it is a request. Ith process is requesting jth resource type. That is what the request edge is. And assignment edge is used to denote the allocated resource for the process. This is also directed edge from R to P. That means from resource type to process. So for example, Rj arrow Pi denotes that ith process is holding jth resource type, or rather in other words I can say jth resource type is assigned, because this is called as assignment edge. Resource is assigned to process Pi. Okay. Any doubt in this? Because anyways we will see example for that. Now let us see the symbol used for this allocation graph. Process is denoted by circle and resource is denoted by say square. So this is process. Resource is denoted by the square and small square inside that. 1, 2, 3, 4 are there, no? Can you see that? These 4 small square inside resource type denote number of instances. So for example, if this square denote say printer, small squares inside that denote that there are 4 printers available. Okay. When ith process request for jth resource, this is denoted like this. Remember, this circle denotes the process. So definitely if you draw something like this, something like P2, this is wrong. Why this is wrong? Reason behind this is very simple. I am writing P2 to represent process 2, and the shape I selected is square. That is wrong. Processes must be denoted by circle. Okay. Let me delete this. Okay. So process PI is requesting for resource type RJ. This is denoted by something like this. And PI is holding an instance of RJ. This is denoted by like this. See, most of the time, if there is only one resource, I'm talking about instance, only one resource for that specific resource type, then the small squares inside that, they are optional. Okay. So here, process PI holds this resource RJ. One of the instances of that is held by process PI. Okay. Any doubt till now? Any doubt in this? Fine. Let us move to the next. Now, this is one of the example of resource allocation graph. Let me quickly ask the question on poll. Have a look at this diagram. Okay. My first question is, let me type it there. Yes, quickly respond to this poll. Look at this resource allocation graph and answer this. How many processes are there in this graph? Okay, last 10 seconds. Now see the poll result. That was very easy question, but still I don't know. 7 plus 3 plus 3. 13 students, they have given wrong answer. Say 60% of the students are correct, 27% not answered it. Why, I don't know. Okay, so P1, P2 and P3, just 3 processes are there, that's it, right? resource type 4 has how many resource type 4 has how many instances? See the results. 58% 28 not answered. So resource 4 is available here. Resource type 4. And there are 1, 2, and 3. So here there are 3 processes, P1, P2, P3. 4 resource types are there, R1, R2, R3, and R4. R1 has just one instance, R2 has 2 instances of that resource, and R4 has 3 instances of that resource. Okay. Now P1 is holding. Let me add one more question. Okay, answer this. How many resources are held by process 2? Last 10 seconds. See the result. Now, interesting part is one of the students says it is 4. I don't know how he counted 4 there. Because if I say there is only one resource that is held by P2, maybe there is a reason. And that reason is there is one outgoing arrow from P2 to R3. Right? Now student saying 2, reason could be like two arrows are coming towards P2. One is from R1, one is from R2. 19% of the students say 3. Maybe reason is like they just counted the arrows, right? But I really don't know why one student selected answer 4. By the way, majority of the students given the correct answer, around 50% student, it is 2. Remember the arrow from, let me highlight it here, the arrow from P2 to R3, this is the request age. Meaning of that is P2 needs resource R3. It is not held by P2. Whereas the age from resource to process, like this one, R1 to P2, R2 to P2, these two ages, that means P2 holds R1 and R2. Is that clear for resource allocation graph? How to read this? That is important. Can you call this as a deadlock? Anybody? Can you call, like for example, P1 is waiting for P2 and P2 is waiting for P1. Is it deadlock? Because that circular kind of thing, you can see it there. So answer to this question is no, it is not deadlock. Let me tell you reason. P3 is not waiting for anyone. See, P1 is waiting for R1, that is resource 1, that is held by P2. P2 is holding R1 and R2, no problem, but P2 is waiting for R3, that is resource 3, that is held by P3, but P3 is not waiting for anything. Remember. So what happens? If P1 is scheduled, P1 will wait there. If P2 is scheduled, P2 is also waiting. If P3 is scheduled, P3 will finish. Once P3 finishes its execution, once P3 finishes, this will be removed. Reason is this resource will be released. R3. Once this R3 is released, what will happen? This arrow will be simply change its direction. So R1, R2, R3, all three are assigned to P2. Now P2 is not waiting for anything. So P2 will finish in some time. Once that is done, all three resources will be released. So this one, and even this R3 also. So P1 was waiting for R1. Once P2 releases it, it will acquire, and P1 will also finish. So remember, this is not deadlock. So fine, today we'll stop here. Let me stop this.